Actually, there's a justify not taking the test. That works too.
Did you ever know that?
The only good thing is that at home
It's just like reviews and I was like slimy.
they have handouts. Start writing whatever is writing down.
I think that's just like one thing for me. What? It's just writing something too. Here, it's like that.
The fuels that we normally use, there's always the potential of trying to find a way to burn them more rapidly. The principal reason we want to do that, increase the flame speed, and reduce the likelihood of knock. Is it apparent to everyone why that reduces the likelihood of knock?
No.
Okay. If you can burn the mixture rapidly, the gases that are under it, which are the ones that undergo knock, don't spend as long a time at the high temperature and pressure. So they can actually go up to the self-ignition temperature and they won't be there long enough for them to ignite and go through knock. So if you burn the mixture more rapidly, you decrease the amount of time the underburn gases see high temperatures and pressures, and it's those high temperatures and pressures in the underburn gases that creates knock. So you got rid of that problem. You reduce the time losses, that should be pretty apparent, right? If we burn the mixture more rapidly, we reduce the time losses? Is there any discussion needed about that? Okay. What I have listed here are the methods that are been used over time, and the methods that are principally used to add turbulence to the mixture. And the more turbulence you add to the mixture, the more rapidly it burns, because you're adding those little small scale eddies such that if here's the flame front, this is burn gases here, unburn. And the flame front is traveling to consume these gases. If you have small scale eddies here, mass transfer actually carries the burning gases into the unburned gases and they ignite more rapidly. So as we add turbulence, particularly small scale turbulence, we increase the flame speed. This can, over a ladder of flame speed, we can easily increase it 3 or 4 times as fast. So what we want to do is get a good look at these various methods. And the ones we'll look at is swirl and squish. These are the ones that are employed very regularly because they're free. You don't have to do any inherent change in the cost of the engine to add swirl and squish. You can lose, you can increase heat transfer, so there are other potential changes to the thermodynamic cycle. But in terms of adding any additional hardware or having to increase the cost of the engine, and that's unnecessary. It's swirl and squish that we first investigated on our lean burn propane engines, and were able to meet the criteria without having to add any cost. We just had to develop the CNC programs to machine the combustion chamber and design the pistons to be shaped appropriately. This is a comparison of what swirl and squish do on an engine. The data is taken under light load conditions. The 2400 RPM, volume efficiency is 35%. So we have not, this is a noticeably throttled operating condition. They're basically comparing 4 different types of cylinder heads. One with squish, one without squish, one with swirl, one without swirl, and then a combination of one with swirl only and one with squish only. In the upper left-hand corner, we can see schematics that show both swirl and squish. As we look in the, see the 4 figures in the upper left-hand quadrant of the paper that was just handed out? In the upper right-hand, we can see the standard combustion chamber. It doesn't have any squish. Just to the right of it, we show the combustion chamber that is squish augmented. The additional squish was shown there schematically in the figure. Everybody recognizes what squish is? As the piston comes up to the cylinder head, if it approaches the cylinder head very closely, typically within about 40 thousandths of an inch or the thickness of the head gasket, it forces those gases in that space to be entered the main part of the combustion chamber. So you see the difference in between, at the very top, on the left-hand side, we have a large clearance in between the piston and top dead center of the cylinder head. And on the right-hand side, it's a small clearance. The clearance is marked C. See the distance there? As the piston reaches top dead center, all the gases that are in between the piston and the cylinder head are forced into the main chamber at a relatively high velocity. When you look at the bottom of the page and eventually get the magnitude of that velocity, yes?
Do those two have 2 different piston heads?
Yeah, you have to change the shape of the combustion chamber. In this case, what they've done is change both the chamber and the piston, so that you end up with a space in between the top of the piston at top dead center and the cylinder head. Here's the combustion chamber. It's a wedge combustion chamber. And here's the top of the piston. As this piston approaches the cylinder head, any gases, as the piston rises, any gases in this volume are forced very rapidly into the main chamber, which adds quite a bit of turbulence. And the mixture burns more rapidly. We'll see how much more rapidly, et cetera, as we go down. This will be quantified, but right now, just in terms of the bulk gas motion, can you see that when a piston comes up and this space goes down to a very small volume, the gases that were here are forced into the main chamber. The rate of decrease in area here is going to be greater than the rate here. And so the gases are going to be forced from this space to that space, and that's squish. This area, here in the cylinder head, is the squish area.
And then the part in the middle, that's the main. The part in the middle, that's the main chamber.
Pardon me?
The part in the middle is the main chamber.
Yeah. Once this is at top dead center, then we have the combustion chamber at top dead center. The piston moves up to this position. At top dead center. And this space is the clearance valve of the combustion chamber. And the gases that were in here have to be forced into the main chamber, and that adds a lot of turbulence. How much turbulence we'll see later down the page, but you can see how forcing the gases from this position to this position, anytime we force gas motion in the chamber, we're going to introduce turbulence. The figure just below that shows a silhouette of the intake ports taken from this view, from the side. And as we lay the intake port down, we have a larger tangential component and will produce more swirl. The swirl is rotation about the center of the axis here. If we look at the view from the top, which is at the top of the page, you can see the intake is on one side of the chamber and exhaust is on the other. So as we lay this intake port down closer to the surface of the page, we're going to get a larger amount of momentum to produce swirl in the chamber. And that's more gas motion, and that increases the turbulence, and that increases the flame speed. So those two methods, squish and swirl, are completely dependent on what shape we have the combustion, the cylinder head and the piston. As we vary the shape of the cylinder head and the piston, we can vary the swirl ratio and the squish tremendously. On the engine downstairs, we went from 0 squish to about 38% or so. And we went from a swirl ratio of about 0.5 to 3.
How do you quantify that?
Pardon me?
How do you quantify squish?
The squishing is qualified by the area, the percentage of the piston that you cover. 39% squish area means that 39% of the piston is covered by the area that comes within 40,000ths of an inch. The squish area is that area in which the piston and the cylinder head approach one another within typically the thickness of the head gasket, which is typically about 40,000ths of an inch.
Okay, so 40,000 is the standard for squisher?
Well, typically, the piston comes all the way up to the top of the cylinder block, and this part of the cylinder head is machined flat because it's economically the easiest way to make the cylinder head. So you make up the squish distance by the thickness of the head gasket, and they are typically 40,000ths of an inch, but you can get them, 120 thousandths. You can buy special order head gaskets at any thickness that you like. You rarely see something under 20 thousandths. It gets more and more difficult as you make the head gasket thinner and thinner to make sure it seals, because it has to somehow take care of any irregularities in the two surfaces. And so it needs a relatively large percentage of its own thickness to make that difference.
What about like O-rings?
Use O-rings, but they're very expensive. They're not used in production engines. High-performance engines use O-rings, diesel engines may use O-rings, normal spark ignition engine, they're too expensive. An O-ring just means that you put a groove in a cylinder block and you place either a metal or in some instances a non-metallic ring in there to seal. And then all the pressure, when the cylinder head bolts bolt the cylinder head to the block, you have a very small area to resist all that pressure, and you get very high pressures and get a very good seal. But it's not something that, it's expensive, so it's not.
So if you were able to pretty much have a port come straight out the top, that would be little to no swirl, and then the more cross flow is.
Exactly. As we look at the cylinder block from the side, here's the intake. The farther it's laid down in this direction, the more swirl we're going to get. Now, what we did with the engines downstairs is we actually, as you look at the combustion chamber from the top, here's the intake valve. We have the port come in like this, and then this side of the combustion chamber goes down. The valve is recessed up into the cylinder head, but the combustion chamber goes all the way down to the squish area on this side, so you prevent the gases from going to that side. When the intake valve's open, they're blocked by part of the combustion chamber. And that's how we got such a high swirl ratio. And how we were able to eventually run lean enough to meet emissions without catalyst. And that's one of the goals that's here, certainly possible with homogeneous charge compression ignition, but for decades, ever since the 1970s, when they started to use catalysts, the intent is to find some way to run lean enough so that you don't have to use a catalyst most of the time, entirely over the thermal driving cycle.
Are you virtually reducing the displacement by adding so much squish, or only increasing the displacement?
The displacement is only a function of the bore of the cylinder and the stroke. So
you're increasing compression ratio, that's what it is.
yeah. And then you have to remove a little metal someplace else if you want the same compression ratio, which is what we ended up doing.
So you end up with a taller chamber and then narrower.
It depends entirely. You can sink the whole chamber into the head if you want to. It depends on where the metal exists in the existing head. If you're casting your own head, then you're free to put it wherever you want to.
Where else is it usually removed from if you're not making it taller?
if you wanna lower the compression ratio?
Yeah, it's going to keep the same compression ratio, but add squish.
You have to look at the particular engine to see if there's metal, if it's a true hemispherical combustion chamber, there's really no metal available to add squish. If you want to, in our case, we started out with a chamber that had a reasonable amount of squish. And then we machined it all the way for the zero squish situation. And then we ended up with the final chamber, we were adding it by cutting the thickness of the cylinder head. And this is at an angle here, so when you plane the head, these distances get thicker. And so, but there's a limit with a given casting as to what you can do. We started out and that's why we ended up with a Mazda cylinder block and a Kia cylinder head on it, because there wasn't any Mazdas that we could find that had metal in enough of the right spots to where we could just do machine work only without welding. And welding becomes very cumbersome. Heads change shape when you weld. Whenever you put a large amount of aluminum welded into a spot, as it cools, it shrinks and it pulls all the metal around it and warps everything. And so you'd rather try to pick some block of aluminum to make a cylinder head out of that you don't have to weld.
What is STD and SW, and then SQ and SWQ?
STD is standard, SQ is squish, SWQ is swirl and squish, SW is swirl. It's just their nomenclature. If you look on the right-hand side, you can see a table that lists the 4 cylinder heads they tested. At the top of the table, it says combustion chamber type. That's the type of cylinder head. It says STD is standard, swirl, squish, and then below that is swirl and squish. And those are the 4 heads. And the swirl ratio given for each one. The standard head had a 0.7 swirl ratio. The high swirl was twice that amount of swirl at 1.4. And that's a ratio of the, when you measure it on a flow bench, that's a ratio of the bulk gas motion down to the tangential gas motion due to the swirl out at the end of the combustion chamber. That's the ratio of those 2 velocities.
How would you measure those?
With the swirl meter in a flow bench. The flow bench automatically gives you the flow rate, you know the cross-sectional area of the cylinder bore, so you know the bulk velocity gas down, and the swirl meter rotates with the speed of the swirl, and you use a strobe to measure how fast it's rotating, so that you're not doing something that slows it down.
So what geometry introduces more swirl?
In this case, the more they lay this port down, the more swirl they get. And that's, in general, the approach that's taken.
I have a question. In the top, we have the 2, I guess, different combustion chambers in which I guess we add squish. Do you either change, like, make either the heart-shaped chambers to just squish, or is that for swirl?
Well, what they've done here is actually, this is a schematic. And what they've done is the heart-shaped chamber, all of that, if you have piston like this and your chamber is shaped like this, then this is all squish area. This is machined out flat with head gasket surface. But they, in the top, they're just dealing with a schematic and they're showing the squish.
Why would you shape it like that rather than
Like this?
flat?
Because you've got 2 valves here like this.
And you just do that to increase squish?
You're making room for the valve. You want to, if you put the wall of the combustion chamber right next to the valve, you prevent any flow as it opens. So that's what we did on purpose to induce swirl. But you want to back this off far enough if you don't want to reduce the volumetric efficiency. So you have to keep this far enough back so it doesn't shroud the input valve or the exhaust. And then in the upper right-hand corner, we've got swirl ratio versus airflow. They were able to get approximately the same swirl ratio in all airflows. That's a desirable attribute. You don't want to have very high swirl at high lifts and nothing at low lifts, because the last gases to enter the cylinder are low lifts, and that puts the gases that have low turbulence near the spark plug, because it's the last gases that enter the combustion chamber after compression that end up near the spark plug. So you'd like to have a relatively constant. That means that the gases also are going to lose less kinetic energy internally, trying to transfer from a high swirl area to a low swirl area. So you can maintain the swirl longer. Remember, you create the swirl on the intake stroke, and then it has to maintain gas velocity all the way through the compression stroke until you ignite it. So you want to develop a bulk flow that doesn't inherently slow down because of turbulence due to combustion chamber and piston top.
So is swirl like angular velocity, is that how it's quantified?
Yeah, no. Swirl is the amount of rotation around the center line of the cylinder.
But it's amount of rotation as in like angular velocity?
Well,
Or is it-
it's the ratio of the gas velocity down to the gas velocity out near the cylinder wall, assuming bulk flow. That's what these ratios are. Okay? That covers about the top of the handout. Is there anything on the upper half of the page of the handout that is mysterious?
Absolutely. You mentioned that you want uniform swirl at different lifts,
Yes.
and you're measuring swirl against flow rate. Are they increasing flow rate by increasing lift? Or are they just-
If you get it during, with flow rate, you've got it versus lift.
Okay.
If you don't have it versus lift, it's not gonna be this flat during, what they're doing here is changing the flow rate. But all the data is taken at just one flow rate on the page. But this is just a demonstration of how well they did their job, basically. If it's not relatively constant during the intake stroke itself, you'll end up with peaks in this curve. If you just go in and start to make modifications that add swirl, kind of willy-nilly, you're not gonna get a nice flat curve like this. And all they're doing is showing here that the swirl that they generated is likely to retain its velocity all the way through to ignition, and the data eventually shows that.
How would you encourage constant swirl?
Well, it depends on how you're making it. Are you shrouding the intake valve? Are you just using a swirl port where the port itself is offset? There are a number of different ways to add swirl, and it would depend on which one of those that you chose, and eventually you show it at the flow bench.
But how would you encourage constant swirl as to?
It depends on which method you're using to develop the swirl.
Could you name those?
Well, yeah, as I said, you shroud the intake valve. And in that case, if the lift is such that you pass the shroud, you have to be very careful that you don't lose a lot of swirl in the process. Can you envision what I'm talking about?
The shroud as in, where's the shroud?
It's the combustion chamber. It's what we were talking about here. You can, which is what we did in the engines downstairs. As the intake valve lifts, you have combustion chamber in the way on one side of the valve to prevent flow from that side, and so you're producing swirl.
Okay,
Now,
I see.
if you can maintain that same amount of shrouding throughout the entire lift of the intake valve, which depends on how high you want to lift it, you can get very consistent values. If you're doing it with an offset intake port, then you just have to vary the height of the valve pocket until you get a good value that's the same all the way across the board. Because at the higher flow rates, the flow field itself is going to change. You can do it with shrouds on the intake valve too,
Probably answered this, but what is
but then you have to prevent the intake valve from rotating. Normally in all engines, intake valves rotate so you get even wear on a seat. If you're gonna put a shroud on one side of the valve, you have to pin the intake valve so it doesn't happen.
I think you had a question first.
I mean, mine's like, yeah, so you have SQ and SWQ and standard and squish. So what is SWQ? Is that squish and swirl, even though they're
Right.
Did it already say
If SW is swirl and SQ is squish, and one of them's got squish and swirl, it's still on SWQ.
So what did, you might have already explained this, but I'm still kind of confused. What exactly about like angling the intake port downwards like that causes the more swirl?
Well,
Is it
look
because
at,
the
look,
angle
yeah,
that
yeah,
it's-
I'm gonna look at the side here. Let's say I have an intake port like this. And I have a valve that's long enough to allow me to do it.
Yeah,
I'm not gonna have much tangential motion in this direction.
because it's coming
But the
straight
more
down.
I lay this port down,
It's coming in like
the
this,
more
which is
momentum I'm gonna have available to create swirl.
Okay.
And so, principally, a good swirl engine is gonna have a much lower intake port than one that's designed for volumetric efficiency. And in general, if all you want is power, you wanna get rid of the swirl. The cylinder heads that, one of my graduate students is working with for the 400 horsepower Miata engine comes with quite a bit of tumble. It flows 211 CFM with a little bump on the intake port and a short side radius here that is smaller than 2 millimeters. You take that off and it goes up to about 240 cubic feet per minute. And the power is linearly related to the flow rate.
What are these two things? Can you re-explain these?
Those are for these go with these to show a schematic for squish. You know what squish is?
Yeah.
Okay, those are shown, those two, together are the schematic that they're using to represent squish.
Okay.
When you add squish, if you have a hemispherical combustion chamber, you can't have any squish if you have a flat top piston. A typical method for maximizing squish is to end up with this shaped combustion chamber, so that you put as much squish area in as possible. And they've chosen that as the chamber that they're gonna call the squish.
Oh, so this is like a raised portion. So that like.
Well,
shaded area-
this is,
Okay.
this surface rotated 90 degrees and sit here.
Okay.
And then, if we've got valves here, we can actually have metal come in this far and still be squish.
Okay.
Couldn't we have squish with a hemispherical engine if your piston is bigger
Then
than the chamber?
the piston has to go up into the chamber.
No, if your piston's bigger than the chamber, then it gets.
Yeah, but Hemis are made like, the purpose for a Hemi is to put a lot of valve in the chamber. So when you wanna use up the full diameter of the piston to put the valves in the chamber. So hemispherical combustion chambers typically have little or no squish at all. They are a slice out of a sphere, it's not Hemi, all the way up to the top, and it fits directly on the top of the board. And that's a hemispherical combustion chamber. You can pinch the sides of the chamber, as Chrysler did eventually with the Hemi that they're making, but it's no longer really a Hemi. Well, their Hemi was never really a Hemi, but they have the name, they have the reputation, people wanna buy a Red-Eye, and so they kept, but that's all in marketing. It's sort of a Hemi in that the two valve stems are not parallel. Okay? Yep.
Sorry, can you explain how does the squish work again?
The swirl?
No, squish.
The squish?
No, piston.
Squish is cause here's the piston before it gets to top dead center. Here it is, the blue line is at top dead center. As it moves up this last little bit, the gases that were originally in this volume are forced into a very, very small volume and consequently are forced out into the chamber, and that's squish velocity.
So that's the top view.
This is a side view.
I can use
Well, for the squish, they give both the side and the top view.
So yeah.
The side view is here, and this is the top view.
And the shape, like the size of or the angle.
This heart shape,
Yeah.
this is the classic shape you end up with when you're trying to add squish to a two-valve engine and maximize the squish. Because all of this area is squish area.
So the more the area, more squish.
Right. Squish area is, you say you have 40% squish area, that means 40% of the top of the piston is covered by that very small gap at top dead center. Okay?
Which side would you prefer to put the squish area if you wanted maximum turbulence? Would you want it on the opposite side from the port or the?
Well, you typically put it, if the port comes in like this, you put it on this side so you don't affect the volumetric efficiency.
Okay. Well, I do it.
See, as we put it over here, we shrouded the side of the valve that flows the most gas. So we're gonna put it on this side typically,
What do you
but
mean?
it's a strong function of where you're gonna put the spark plug. Because if you have one spark plug, or if you have two, but if you have one spark plug, that dictates where the flame is initiated.
So that shaded portion is a squish area, right?
Well, if at top dead center, you have a piston like this,
Yeah.
then this is squish area and this is squish area. Wherever the piston comes up to the flat surface in the cylinder head,
Yeah,
there's machine flat, that's squish area.
I get that, but I'm talking about that schematic, that shaded portion.
This one? Yeah, this is squish area.
Okay, yeah.
Yeah. And in a classic case, when you're trying to maximize squish area, and we have gases flowing in from an intake port like this, we're going to put as much area as we can here, because if we inhibit the flow on this side of the valve, it's not as detrimental to airflow as on this side of the valve.
Oh, okay.
And then the spark plug is gonna be over here somewhere. It depends on whether it's a cross flow head, you have an exhaust out this side or this side, but I'm assuming it's not a cross flow head.
When you're designing a cylinder head for better swirl, you're also reducing the volumetric efficiency, right?
Absolutely.
So you're making less power because you have less air, but you're also making enough for some portion of it by using swirl. So does it you end up having less power but better efficiency?
Yeah, you typically end up with less power and more efficiency. In the last iteration of the engine downstairs, we went from a 1 1/4 inch intake valve to a 1 1/2, so that we got all the power back. But now you have to pay for a valve that's a 1/4 inch bigger in diameter. And you have to have room in the combustion chamber for it, which we found in this case. It also allowed us then to have virgin metal to cut for that shrouded portion.
So is there an upper limit to squish area that's been found? That
Well, yeah, it can't go above 100%.
Oh, yeah, like, I meant like a 40, 50.
You could design 100% if you wanted to, but you'd have a compression ratio that'd be so high, it'd be, then the entire height of the combustion chamber is 40 thousandths of an inch. So if your stroke would have to be 4/10 of an inch for 10-to-1 compression ratio. So there are sort of upper limits, but realistically, you hardly ever see, 40% is a monster number. And we've got high 30s in the last engine we built to extend the lean limit down to where we can meet emissions. And then we had to put in a bigger intake valve because we'd added so much swirl that we lost so much volumetric efficiency that the column was way down.
By putting the squish on the side that you said wouldn't be beneficial, you would probably produce more turbulence than because it's.
By putting the squish here,
Yeah, because
it's
you're.
pretty much a function, as you'll see at the bottom of the page, of the squish area. The gas velocities are, it's just, you put it both, if what you really wanna do, and what we ended up doing, we put it in every spot we could find. We ended up with, here's the combustion chamber, we had a area like this, here's the intake valve, we had another little bit over here, another little bit over here, wherever we could put it in. And, the spark plug, the exhaust is here, and the spark plug is located about here, in the best chamber that we had for the, generator engines. That same, that started as an automobile engine, put it in a car, and it would just blow up. You change enough of the design considerations to where it's no longer at all usable for an automobile. As I said, if you just use it as an automobile's generator engine, it only delivered 29.4% thermal efficiency. After it's modified to specifically be used as a generator engine, it was 37.5, and it didn't cost any, we could have rebuilt it as an automobile engine for about the same $1,500 it cost to rebuild it as a generator engine. Once it's designed as a generator engine, it no longer can function as an automobile engine.
Is this because of you don't pass a certain RPM, or why is the reason why you couldn't use it as an automobile?
Well, the RPM limit, that's one limit. We went up to 12.71 compression ratio, knocked another limit. We use smaller journal bearings to reduce friction because we're only at 1,800 RPM, they would tear up at higher RPM. We used lighter valve springs, there's only an 1,800, so all the valves that floated at higher RPM. You get through doing this with accelerator valve once.
If you could use it on an automobile below 1,800 RPM, it would be fine.
No, not at 12.71, not with normal gasoline. You could use it with E85, the spark could be all wrong. You could find some condition that's just like the generator, 1,800 RPM cruise, but you're gonna need a fuel with as high octane numbers as propane. And to do that, you'd have to be down at a few stations that sell E85.
Now, by increasing the squish area, obviously you have more edges. Does that affect the hot spots?
With aluminum, well, either cast iron or aluminum head, it's not particularly a problem. You get a hot spot when you leave a sharp corner. You know, the piston comes to a corner like that, now it can get hot. But as long as you don't leave sharp corners in the combustion chamber, even with cast iron, you really don't have a problem. You can have a problem near the exhaust seat, but that's because during the exhaust process, the initial blowdown process, there's a huge amount of heat transfer. The gases are passing that area at the speed of sound, they're very high heat transfer coefficient, and they're at their hottest temperature. After blowdown, the gases in the cylinder are now at a lower temperature, because they did all the work to force the other gases out at the speed of sound. So, you can, and when you have heat problems like that, and the electrode and spark plug, if you get the wrong design spark plug, it's just a little wire that hangs out of the chamber, it can overheat. Even the ground electrode can overheat. But those are all, the spark plug components are highly insulated parts. And the exhaust valve experiences heat transfer way above any place else in the chamber. It's always the hottest general area in the chamber. You can find spots in the spark plug that may be a little bit hotter. The exhaust valve is going to be hundreds of degrees hotter than the rest of the chamber. The actual metal in the chamber maybe goes to 350 degrees. The intake valve could possibly get there, and exhaust valve easily goes 1,400 degrees. As I said, if you put a window in the exhaust and look at it during operation and go to, as you open and go to high load, the valve begins to glow, turns orange. You know, now that's still, it's not gonna melt for another 1,000 degrees Fahrenheit, but it's quite hot.
What would you say are the main pros and cons of increasing squish area?
The main pros and cons?
Right.
Well, what we're doing here is increasing the turbulence. So all of the positive effects of increasing flame speed exist. You have all the negative effects of increasing flame speed, which is heat losses, exist. So it's everything everything is normally in the course.
I thought you reduced heat loss.
Yeah, are
Okay.
there like mechanical?
I mean,
I thought you reduced heat loss.
yeah.
Would an engine with a smaller stroke also have a higher swirl ratio typically?
A higher one?
Swirl ratio, if you have a shorter stroke?
No, it's typically how you've designed the delivery of the gases to the chamber, which is the intake port and the combustion chamber around the intake port, and to what degree you've shrouded valves. That's what produces a given amount of momentum that can be used to produce rotation.
Oh, yeah.
And so, you can, it's not particularly a function of the cylinder themselves.
Wait,
But you said it's a ratio of the tangential velocity to the vertical velocity, right?
Yeah, but you don't have a good amount of momentum, so it slows down when you spread it out over a larger diameter.
did you just say when you increase flame speed, you increase heat losses?
Pardon me?
When you increase flame speed, you increase heat
Whenever you
losses?
increase turbulence, you increase the heat transfer coefficient between the gases in the middle, and you get more heat losses. Which is what we'll see as we go to the next page in a handout.
So then that reducing knock, a potential to reduce heat losses?
Well, if you have a way to reduce knock, you can better insulate the combustion chamber and reduce the heat transfer, because you don't have to worry about overheating the unburned gases and producing knock.
So that's not a direct correlation with increasing flame speed? That
Well,
reducing knock
if you
is-
take advantage of
Okay.
the knock reduction, then it is.
So would that be
If-
like you would change the geometry of the combustion chamber to do that?
Well, there are a number of coatings available
Okay.
that companies advertise do the job. By the end of next semester, we'll have some of our own data to see, it's kind of questionable. Ryan and I have been looking at it, and it would appear that what they've got should be. But time will tell. We're setting up an apparatus to where we can look at heat transfer in the exhaust port, and if they work in the exhaust port, they probably work in the combustion chamber, but that would be another project. Okay. So we've looked at sonic throttling intake valves. Swirl and squish, we can see here In the middle of the left-hand side, these are the gas velocities measured near the spark plug for the swirl head that has a swirl ratio of 1.4, and the standard head, which has a swirl ratio of 0.7. Those are the actual gas velocities over the entire intake stroke there. Is that clear, the 360 degrees there? Starting with the intake, and then, of course, for the second half of that, approximately, we have the compression, and the swirl rate is still dropping in the chamber, but what we want to do is maintain enough swirl to where, at the time of ignition, we still have some swirl, which is what's done here. And at the bottom, we can see the gas velocities created by the squish. We have the standard head, which has some squish, and then we have the augmented head, and we can see at the neighborhood of 15 to 10 degrees before top dead center, we reach maximum squish velocities up at about 15 meters per second.
What is this, bottom left?
Bottom left hand, you see there's a little schematic of squish there. You can see the crankshaft, the little arrow shows its rotation. The piston hasn't reached top dead center yet, but they have squish velocities drawn in 4 little arrows, VQ. So basically, swirl, which is produced on the intake stroke, diminishes with compression. Squish is added only as you begin to approach top dead center, very late in the compression stroke. Because you have to have a large ratio in between this volume change and this volume change. And that ratio gets larger and larger as you approach top dead center. If this volume changes more rapidly than this volume changes, then the gas is flow this direction.
So, you mentioned the squish area too, but like that depth between the, like that little, not that one. Yeah, but just that one portion in the actual piston head, like that dip.
Yes?
Yeah, how do you determine how high you want that to be, or like how deep you want
Well,
it to be?
of course, there's a given volume you have to get whatever compression ratio you want.
Yeah.
And that's the principal determining factor. And the more of the combustion chamber you put in the piston, the higher the heat load on the piston. So the higher the high performance engine, the less you want to have an actual dish in the piston, and all of our engines downstairs just have flat pistons.
Okay.
That's the minimum surface area, and we design the rest of it around the flat top piston.
Does squish have an effect on the exhaust stroke?
In what way?
Does it improve the exhaust?
Not in any noticeable fashion, no. The gas velocities are important because of the small scale turbulence that they produce. But they don't show up in terms of improving the scavenging or hurting the scavenging. So the data all on the right-hand side and then the top left, all on the left-hand side and everything on the top right-hand side explains the behavior we see at the bottom quadrant of the handout. We see 2 plots here. We see minimum best torque spark advance there at 30 to 40, 50, or 60 degrees before top dead center. And we see air-fuel ratio. 15 to 1 is about stoichiometric. It's a little bit leaner than stoichiometric. And we go all the way out to 19 to 1, which is very lean. And we can see the standard cylinder head requires the most spark advance. And if we look down at the bottom, we can see the standard cylinder head is the least efficient. It has the highest rate-specific fuel consumption versus air-fuel ratio. The little symbols that look like this, the line with this, that's the lean limit of combustion. You cannot ignite the mixture when you've leaned it out that far. And you'll see as we add turbulence, the lean limit of combustion moves to leaner fuel-air ratios.
What's MVP again?
Minimum best torque spark advance. Remember, if you pick exactly the right spark advance to produce the most torque, you can retard that generally noticeably and reduce the likelihood of knock without losing much torque. So they affix maybe a 1% or a 2% loss torque, and they retard the spark from the absolute best efficiency spark advance. And that's minimum best torque spark advance. we can see here adding swirl and squish requires the least amount of spark advance, which means that the time losses are minimized, and that produces the best thermal efficiency as we look at the bottom. You can see the same symbols that exist in the figure, of the two figures in the lower right-hand side, the same symbols are used at the top and the bottom. If we look at squish only does not augment, doesn't reduce time losses as much as swirl for this particular combination of squish and swirl. If we look at the bottom, we can see the trend changes at about, say, 16.7 to 1. And if you're richer than 16.7 to 1, you're better off with squish, but if you're leaner, you're better off with swirl. It should be obvious from the data on the rest of the page why you'd expect a transition like that. It's a function of when you add the turbulence. With swirl, you add it early in the cycle, and then it decreases. With squish, you add it very near top dead center. So if you already have a relatively high flash speed so that you don't have ignition problems, you can add squish and get a further improvement in efficiency. But if you've gotten so lean that you're having ignition problems, the leaner the mixture, the earlier you're going to ignite it and the more intense the swirl. So for the very lean mixture, swirl is favorable. That's why they cross. They're going to have to cross somewhere. It happens for this combination of swirl and squish that cross occurs at 16.7.
So you said swirl happens later?
If you look at the figure on the left-hand side, you can see on the left-hand quadrant, we have when the velocity of swirl occurs and when the velocity of squish occurs. And the swirl is highest during the intake stroke itself. And then it decays during the latter part of the intake stroke into the compression stroke. It continues to decay, and eventually is a small value at the time of going to ignite the mixture, but still sufficiently large to promote combustion. The squish, on the other hand, is rather small. We see very little effect until we reach about 30 degrees before top dead center, and then it's maximized in a range of 10 to 15 degrees before top dead center.
So that's squish and swirl. Or it's SQ.
The curves that are dotted there are the squish intensities only. You can see the one marked SW and standard. That's from the tail of the figure above it, in between 30 or 50 degrees before top dead center. That's just a duplication of the data above it. And to get the total gas velocities, you'd have to add the swirl and the squish together.
So
Can you re-explain the intersection with the VSFC and the air-fuel ratio?
Yeah. If you see that, what is the spark advance for these lean mixtures? And here it's 17 to 1. What type of spark advance with either swirl or squish is being utilized? At 17 to 1. We're anywhere between 40 to 45 degrees before top dead center.
Yeah.
Now, if you look at the figure on the lower left-hand side, in between 40 and 45 degrees top dead center, squish really hasn't added much turbulence yet. Some, but not a lot. Consequently, you're not going to expect a really big result. But the swirl has added even more turbulence than it adds at 30 degrees before top dead center. So it's definitely more useful for the higher spark advances, and that's what you're going to require for the leaner mixtures, which burn slower.
So the dotted line on the bottom left that says SW,
That's a duplication of the data for the figure just above it that's called SW for the dotted line. And then the one marked standard is a duplication of the data just above it from the far right-hand side of the data just above it. And you would add onto those velocities the squish velocities to find the total squish. And what's been shown in the figure in the very lower left-hand corner is the squish velocity, how much you would add. Yes?
Would swirl be more beneficial at higher RPMs because it's still like at a lower RPM, it has time to slow down or like kind of, because you close the intake valve and then it cuts
Well,
off.
yes, at higher RPM, the squish velocities go up dramatically. So it really depends on the fuel-air ratio that you're talking about. And the squish is still, at very lean mixtures, it's still useful. You can see that compared to the standard on the figure in the lower left-hand corner, but not near as useful as the swirl. And the swirl is gonna tend to be more useful for lean mixtures where you're gonna be igniting it much greater distance before top dead center, whereas the squish is gonna be most useful when it's most intense, which is much nearer top dead center. So if you have a rich mixture, you're not gonna use near as much spark advance. You can see that in the figure. Even the standard is only about 45 degrees before top dead center for the spark advance, if you're talking about 15 to 1. It's increased to over 60 to 1 if you're talking about near the lean limit at leaner than 17 to 1.
So when you say more intense, what do you mean for squish? You said squish is preferring more intense.
Squish is going to be more useful if you have richer mixtures. Swirl is more useful, as you can see depicted in the lower left-hand corner here. You can see the best brake-specific fuel consumption when you compare swirl and squish occurs with the swirl for the lean mixtures and the squish for the rich mixtures, and the crossover occurs at that about 16.71, which is, for a conventional engine without a lot of modification, about as lean as you want to run normal.
What's the vertical bar here? I know you talked about it.
Yeah, that's the lean limit of combustion. This symbol means that if you go leaner than that, which is to the right on your figure, you can't ignite it. It's no longer ignitable. Adding turbulence, to an extent, extends the lean limit of combustion. You can run a leaner mixture after you've added turbulence.
Why?
If you add, well, that original, as long as you don't add so much turbulence that you put the original flame kernel out, you make it grow faster. But it's just like blowing a match out. If you overdo it, you get to where, when the spark is ignited, there's a little ball of flame that's created by a little ball of hot gases that are way hotter than they'll ever get in combustion. The arc, the electric arc is at temperatures much, much higher than the temperatures reached in combustion. So you end up with a little sphere of burning gases. And then the ignitability is determined by how rapidly can that increase in diameter. The more rapidly it can grow, the more repeatably will be the growth. And if it's not very repeatable, if one time it grows slowly, and the next time the engine rotates twice, it grows rapidly and slowly, that hurts efficiency a lot. Okay, are there any questions there on this? Okay, well, that's some of the behavior of swirl and squish. We have multi-point ignition as possible. And we have an effort here done by the sun in which they took it to an extreme and made a plate that fits in between the cylinder head and the block that contains 12 ignition sets. And so what they, this is a duplication right here. They just replotted it for you. And having discussed swirl a bit, we're now going to compare multiple ignition sites to swirl. Remember, as we add swirl, we can burn the mixture more quickly, which reduces time losses. but we're going to increase heat losses. As we go to multiple ignition, the increase in heat losses is much less, but now we have to pay for a more complex ignition system. And so, what you see, the figure at the top upper left hand is that plate that goes in between the cylinder head and the block with the 12 ignition sites, 6 on each side of that combustion chamber, which has squish on what is now the top and the bottom of the chamber. What they show to the right of that is the fact that they had to use a higher voltage. They used one voltage per side, one big coil per side to ignite all 6 gaps. And so when they only had to fire one gap, it took in a neighborhood of, say, about 8 kilovolts.
Wait.
And by the time they fired all 6, they were up around 14.
Does like, do you mean that one spark plug has multiple gaps? Like, what do you mean by
And
that?
what they've got is a piece of metal with a porcelain electrode around it, and then at the top they have a electrode that looks like that. The one next to it looks like this, and the porcelain here to insulate it, and the gaps in between here and here. Then they have another one here. And so now we've got 2 gaps. And they continue until they got 6 gaps.
Are they all connected to the same coil for a cylinder?
Pardon me?
Are they all connected to the same coil for a cylinder?
Yeah, when they connected them all to the same, each side to the same coil, the voltage required is what you see in the upper right-hand corner. Because there's interest in, you know, how much are we gonna have to increase the cost of the ignition system? Well, that's a function of how much voltage we need to gap the plugs. And now with the 6 gaps, we've got in the neighborhood of twice as much voltage necessary.
Wait.
On the right-hand side, we can see for the engine running with a variety. Now, they're using a schematic to indicate how many spark plugs are actually firing. Here's the combustion chamber. Remember, there's 6 sites here and 6 sites here available for them to fire. They can short some of them out so that they don't fire. And this means that 4 of them are firing in the 4 corners. This would be 4 of them on one side are firing. But you can tell from the schematic how many of the plugs are firing and what their location is. And the schematic is shown there next to the brake-specific fuel consumption curves. And then above that, once again, is the spark timing. And we can see with one spark plug, we need the largest amount of spark advance. And then as we increase the number of plugs to 2, to 4, to 6, and finally 12, the amount of spark advance decreases. Yeah.
When do they ever use that many spark plugs?
This is just a prototype engine to see how viable it might be. And they use 12, which everybody knows is way too many, to see what happens when you extend it well past what a reasonable number of spark plugs would be. And we see here that doing so actually hurt efficiency. When you compare the 6 to the 12, when you have very lean mixtures, you get better efficiency with 6 than 12. The problem is with multiple spark plugs here, as these flame fronts begin to grow, they overlap. Once they overlap, you're not getting any additional advantage to the multiple ignition sites, because eventually you're gonna have a flame front that looks like this, which is not so much difference in area from the single plug. And we'll see that as we go down the page on the left-hand side, that, on the right-hand side, that there's very little advantage to going to 6 plugs on one side of the combustion chamber.
What?
Is there a
Question.
disadvantage or a little advantage?
Pardon me?
Is there, it looks like there's a disadvantage, or is there?
Not a disadvantage, just a small advantage.
Could you re-explain?
When you compare 6 plugs to 1.
Oh, 6, what about 6 to 12?
Well, then the 12 is a disadvantage.
Right.
And you can see that in the second figure from the top on the left-hand side, the brake-specific fuel consumption for the very lean mixtures with 12 plugs is worse than the brake-specific fuel consumption for the 6 plugs. And that's because, as I said, when the plug fires, you raise the temperature of those gases well above whatever combustion would take place, and that original flame kernel grows because of the high temperature gases, trying to expand, and that creates turbulence at the wall, which increases heat transfer. The difference in between 6 here and 3, these overlapping frame fronts are not able to decrease the time losses enough to make up for the increase in heat losses that occur because we've ignited all of these and have these expanding original flame cones. Question?
So what's the most common? Is it two?
Pardon me?
What's the most common?
One common is one.
This is an investigation. Not all engines have one, but the most common is one because it's cheap. And this is an investigation so that they would know as they go to multiple spark plugs, what type of advantages can be had. Now, they've missed the principal advantage in terms of reduced unburned hydrocarbons, and we have an engine downstairs being designed with 4 spark plugs that should cut unburned hydrocarbons at least in half. They noted a decrease in unburned hydrocarbons, but they positioned the spark plugs such that they were nowhere near maximizing that advantage. And in the paper itself, they attributed the reduction in unburned hydrocarbons we see at the bottom of the page more to the time in the cycle in which the gas is burned, which is in effect than to the unburned hydrocarbons caused by the crevice volume between the piston and the cylinder wall.
Like I was saying, you already have less hydrocarbons with 6 than with 4, sorry. Yeah, why is that trend?
Well, let's go ahead and go down the page so we're not missing a lot of stuff. If we look at the second figure on the left-hand side down, we note that as we get very, very lean, all of a sudden, the best efficiency spark advance doesn't increase. You see how the figures go like this, and then they flatten out?
Yes.
Particularly with 1 spark plug?
Is this figure A?
Well, what's happening here? Yeah, well, or figure C, depending on, you know, if we call that figure A, then there is no figure letter for the one at the top.
Oh, so E. Okay.
But I think we're all looking at the same figure, and that's what counts. If you look at the spark advance, particularly if a 1 spark plug goes like this, then it flattens out. This is best efficiency spark advance versus fuel air ratio. We leaned it out, the inherent flame speed went down, but it didn't like more spark advance.
not seeing this one.
What's happening here is we're avoiding not being able to light the ignition at all.
I'm not seeing this flat.
See, as we go to here, we go to
No, wrong.
lower and lower temperatures and pressure at ignition. And we reach a point in which, if we chose the optimum spark timing, the temperature and pressure at the point of ignition is so low it wouldn't ignite at all. So you reach a point to where you can't go far. You can lean the engine out more, but you're not going to add more spark, even though the engine would be more efficient if you could. But you're adding that additional spark advance. That means you're trying to ignite a cooler, lower pressure mixture, and it won't ignite. So the flattening of those, particularly for the single plug type of operation, and it gets a little bigger, a little better as we go to more multi-plug operation. But we've already discussed why the 12-plug combustion chamber doesn't deliver as good efficiency as the 6-plug at the lane mixtures. And so if we look at just to the right, we can see the stability. That's a function of how repeatable each cycle in a given cylinder is. If every time that cylinder fires we get exactly the same behavior, then there's no fluctuation in torque. But if it changes, we can measure the fluctuation in torque, and that's what's shown here. And as we get leaner, the torque fluctuation increases. With a single plug, it increases rapidly, and of course, that means the cycle-to-cycle variation is larger. If we drew the PV diagrams, they would not look, one cycle would not look like the next one at all. And this could be improved even as we go all the way out to the 12-plug operation. And that inherently is going to give us a better thermal efficiency. What's shown in the figures that are third down from the top, both on the left and right hand side, is a comparison with 1 plug and with 2 different geometries for 6 plugs. And clearly, the 2 different geometries for the 6 plugs are to either put all 6 plugs on one side of the chamber, or spread them out like this, and of course, this gives much better thermal efficiency. Because here, these flame fronts overlap very early in the cycle, and we can see the actual flame front area as you look at the figure on the right-hand side. By the time you've burned half the mixture, the flame front area is the same with either 1 plug or all 6. So the only advantage in terms of enhanced combustion, in terms of the rate of combustion, with the 6 plug occurs in the first half of the cycle, is small. On the other hand, in this case, when the flame fronts have grown this big, they're still not overlapping. So the total flame front area is all of this area. Okay? And this continues until eventually they do overlap. And you can see then that we can go to a much leaner mixture with the 6 plugs laid out like this. And the efficiency is going to be higher. Yeah.
Are there no lean limits of combustion in these?
They're no shown, you'd have to take them off the previous figure.
But why is it so much leaner with these than the previous?
Well, this is an entirely different engine than previously. And the load conditions are different. This is already under a higher load. And the more power you're taking out of the engine, the easier it is to go to the later registers. And at the bottom, we can see that the unburned hydrocarbons change depending on spark plug location and number of spark plugs. And principally what's happening here is these are, since they haven't tried to position the spark plugs to fill the crevice volume between the piston and the cylinder wall that contains a lot of unburned hydrocarbons that come out later in the cycle. The principal thing that is occurring here is when you're actually quenching the gases. As the gases burn closer and closer to the cylinder wall, the hot gases are transferring heat into the unburned gases, the cylinder wall is transferring heat out of them. And eventually you get close enough so these the relatively cold cylinder wall is cooling these gases to the extent that you can't burn them, and they're quenched. Quenched means we don't burn them. And so if you quench them early in the cycle, this same volume of gases, and actually early in the cycle, the quench distance is a little bit larger, but not enough to make up for the fact that the gases here are in much lower concentration than they are late in the cycle. So the quench that occurs late in the cycle, after the flame front has traveled across the combustion chamber, is going to produce more unburned hydrocarbons.
So all of these are 0 squish, right? Because you can't have any squish with 6 spark plugs like that.
No, they did. This is all squish here.
That makes sense.
That plate goes in between the cylinder head and the cylinder block. The piston comes up the top dead center, and this is all squish. How much swirl they're not even mentioning.
Okay.
But the principal criteria here, the comparison is the number of ignition sites. That's what they were worried about, and they chose to do it in this fashion. If they had done it without the squish, I think they would have had even more startling results. That's the engine we're building downstairs, one of the engines. That's the engine that General Motors is using.
So if you had like if you had 2 spark plugs and they were offset and you had it shrouded, could the flame kernels themselves like create some swirl and turbulence just because you've got like an unequal pressure?
The flame kernel just expands basically as a sphere unless you have a huge amount of swirl, and then it's a sphere that's moving downstream with the swirl. So it's very difficult to try to create, with a combustion process, any sort of a bulk rotation. There's no way to push against something with a combustion process so that you could provide preferential gas motion.
Like if you would have your spark plug, let's say where this heart-shaped chamber, you would have your spark plug on where your intake valve is right now.
The spark plug is typically.
It's usually there, it's either, but if it were to be where your ignition, where your intake valve is, could the expansion of the gases push the other gases around and create more turbulence? I think
That's kind of.
that's kind of what he's asking.
Not to any appreciable amount. Remember, this quench just only exists at top dead center. As you begin to open it up again, this volume gets larger. The, you can't really create swirl, any appreciable amount of swirl during the combustion process. The swirl occurs beforehand, and then the combustion goes right along with it. In other words, if viewed from the top, we have a high swirl ratio on this, we have a spark plug here, flame turtle can grow like this, whoops. And this side of it never progresses, because you're feeding in more air on this side, and the center of the sphere is just moving with whatever the rotational speed is. But remember, you can't get pressure gradients with combustion. The flame speed, unless it's knocked, the flame speed is not high enough to where the perturbation that creates the pressure rise travels throughout the entire combustion chamber far more rapidly than the flame speed. So when you do a PV diagram, if you have knock, if you don't have knock, it's a nice smooth curve. The only time you see this is when you do have pressure gradients, and at that point, you did it with knock, and you have to back off the boom. Good?
Dr. Swain,
Yeah.
are you familiar with the Chrysler Crossfire and how it has like multiple spark plugs? How does that work? Like, is this one of these sort of configurations, or it's just like one on each side?
Chrysler's the one company that's been going to 2 spark plugs, and all that does is allow you to double the flame front area. And the marketing can call it what they want, but fundamentally, all the advantages of 2 spark plugs you get, which means you can burn the mixture more rapidly, you can go to higher compression ratio because you're less likely to knock. You can reduce the amount of cooled the engine, reduce the heat losses, all the inherent advantages you get from the rapid fire.
Are spark plug geometries generally considered in surface volume ratios, or is it kind of ignored because of?
The spark plug itself,
Yeah, like the metal sticking
yeah,
out.
you can add in that surface area,
Mhm.
but it's small compared to the total surface area of the combustion chamber. And what you have in the spark plugs, if you cut the spark plug open here, we have a center porcelain core to insulate it to make sure that we don't get a spark jumping from this, which is the cylinder block. We want to jump over to the center electrode. We don't want it to jump inside here. We want it to jump outside here. And the heat range only changes how far this porcelain goes toward the tip. As the porcelain is fabricated closer to the tip, you've got a colder spark plug. And as it's farther away, you've got a hotter spark plug. And that's principally it. You can buy spark plugs that have like 3 ground electrodes, but it's very debatable as to, the manufacturer will say wonderful things. You put them in, those don't touch things. Okay, so basically, if you have 1 spark plug, what they're saying in the figure in the bottom is you're delaying the quench, because that flame front reaches the other side of the combustion chamber. And when you delay that quench, you're quenching gases that are much denser, so you get higher unburned hydrocarbons. The quench distance is a little bit thinner, but not thinner enough to make up for the increase in density of the gases. So that's what increases for the minimal spark plugs, increases the unburned hydrocarbons.
Can you say the beginning of that again?
Yeah. When what creates the hydrocarbons is quench. If you have spark plugs on both sides of the chamber, the quench occurs early in the combustion process, and then the gases burn toward the center where they're not quenched. So as you quench the gases late with a single spark plug, goes all the way across the chamber, now you're quenching gases at the highest temperature and pressure, so those gases are very dense. They contain a lot of fuel in the same amount of volume. When they're quenched then, you get higher unburned hydrocarbons.
When they're quenched late, you have?
Yeah, yeah. Because when they quench late, they're at a higher temperature and pressure, and they're at a denser, the concentration of gases in the quench layer, there's more fuel and air in the quench layer. Same ratio of fuel and air, but there's more of it because it's at much higher pressure.
Could you re-explain quench? Like,
Quench?
yeah.
Well, You ever blow out a match?
Yeah,
That's quenching.
cool.
You're quenching. You added enough cold air, which you could have used to oxidize, so that you drop the temperature